So this base can be explained with the help of Bronsted acid-base concept. Now let me write some more acid-base reactions. Okay, so suppose I write, suppose if we have a hydrogen fluoride and in presence of H2O, suppose this is acid, I am writing the acid-base reactions, acid-base, and this is the equilibrium reaction suppose. So this forms the H3O plus and plus fluoride ion. Okay, so this is acid, and corresponding to this acid, when acid lose a proton, when acid after losing a proton, what is left, that is called as the conjugate base. So that's why this is conjugate base. And what is formed when base gains a proton, when this base gains a proton, and what is formed, and that is called as the conjugate acid. This is called as the conjugate acid. Okay. Similarly we can write these other reactions. Suppose if we write here this H2O, so HF here, sorry, HF, it acts as a strong acid, and this is a this weak base, and corresponding to this strong acid, one of the conjugate base is formed, which is a weak one. So how this is weak, how this conjugate base is weak, that we are going to discuss. Now before that, so next let me write another reactions. Suppose this here this H2 acts as a base, and this H2 acts as the acid, because we know this water acts as a acid as well as base. So in this reaction, so this will act as a this will form a H3O plus this OH minus. Similarly, suppose if we have ammonia plus water, that may form, okay, so after losing a proton, this acid, this is a weak acid, suppose here, this is a weak acid, ammonia acting as a weak acid here, and after losing a proton, it will form a conjugate base, and which is a strong base, and plus this acid is formed. Similarly, if we have a CH4 being a weak acid, after losing a proton, which is formed, after losing a proton, what is formed is CH3 minus. This will act as a strong base plus H3 plus. Now, so these reactions I have written, and from this reaction we can find the this Ka, and Ka, it tells about the strength of acid, and indirectly we can say the strength of base can also be found out. So we can write the Ka, that is the concentration of this multiplied by concentration of this, divide by concentration of this, multiply by concentration of this. So for all this reaction we can determine the value of Ka, or we can determine the value of, indirectly we can also say that we can determine the value of pKa. We can determine the pKa, and pKa, we know that this pKa tells about the relative strength of this acid base. So relative strength of acid base, that can be determined with the help of this pKa chart. And if we see, then which reaction out of this 4 reactions that I have written, which reaction is more favorable? No doubt, reaction which is going in a forward direction is more favorable. So which reaction is favorable in the forward direction? No doubt, that reaction will be favorable. Which forms the stable product in forward direction? Reaction which forms a stable product in a forward direction, that would be the favorable reaction. Now, which is favorable? Which is the stable? So, out of this various negatively charged species, 4 negative charged species, which is more stable species? So, as this is a base, this is a conjugate base. So, conjugate base, and which conjugate base is more stable? Which conjugate base is more stable? So, means which negative charge species is more stable? So we have to determine, we have to find out which negative charge species is more stable. So species, the negative charge species which is more stable, that will give you the most favorable reaction. Okay, so that will give you the most favorable reaction. So indirectly what I have told, we can determine the value of K, or we can determine the value of pKa in this reaction. We can determine the value of pKa of this reaction. So indirectly what we can say, we can determine the strength of acid-base reaction. So in acid-base reaction, we can determine the strength of acid-base reaction, or we can determine the stability, relative stability of acid-base. So here we can determine the relative stability or relative strength of acid-base reaction by knowing or by determining the pKa value. Okay, by determining the pKa value, and this lower is the pKa value, higher is the acidic strength. We know lower is the pKa value, higher is the acidic strength. Okay, and so this will give you the relative strength of this acid base, or this will give you the relative stability of this acid base. So which is more stable? Here, which conjugate base is more stable? That what are the factors which tells about the stability of conjugate base? Means more stable is the conjugate base. Stable is the conjugate base, weaker will be the base. So I will tell you later, I will tell you the various factors which determine the stability of this negative charge. So but here in this case, this is most stable. This is most stable conjugate base, and that's why this is the weaker one, weak base. This is the weak base, and here this is the most stable, and this is least stable. This is least stable base, and it is the strongest base, because if base is least stable, if anything is least stable, then that would be more reactive one. So it is most stable, that's why it is a least reactive base. It is a weaker base. In the same way, so this is the strongest acid. So strongest acid is giving you the this weak base. So strongest acid after reacting with water is giving the most stable base. So that's why most stable product is formed here. Here least stable product is formed. So no doubt this reaction, this first reaction is the most favorable reaction in forward direction. So that's why we can write in this way. This arrow can be written in this way. This reaction is most favorable in the forward direction. Whereas if you see this reaction, and this reaction is less favorable in the forward direction, or this is favorable in the backward direction. So we have to see what are the factors which affect this stability of this conjugate base. So one thing usually students are confused. Students think that the strongest acid are the weak base. What we can see here, strongest acid, it is giving you the weak base. This is strongest acid, HF. It is a weak base. But this is the misconception. So what is the usually misconception? Misconception is that strongest acid are weak base. This is a very big misconception. Strong acid are weak base. But this is not correct. This is not correct. Strong acid are not always weak base. If you see CH4 is a weak acid. CH4 is a weak acid. So weak acid should be the strong base. So this weak acid is CH4 is a weak acid, but CH4 is not a weak base. Weak base is CH4 is a weak acid, and weak acid, that is a strong base. But this CH4 is not a strong base. CH3 minus is a strong base, which is a conjugate base of this weak acid. So what is the correct statement? Correct statement is that the strong acids have weak conjugate base. Strong acids have weak conjugate base. Weak conjugate base. Or we can say that strong base have the weak conjugate acid. Okay, so for example, if CH4 is a weak acid, if CH4 is a weak acid, then this is not is a weak base. This is not a weak base, but it's a conjugate. It's conjugate base, that is CH3 minus. CH3 minus is a strong base. So weak acid, this is the strong conjugate base. Okay, weak acid, strong conjugate base, strong acid, weak conjugate base, and vice versa. Okay, so this is the usually misconception. Students has a misconception, and that should be cleared. So what are the factors? What are the factors which affect the this stability of this base, or what are the factors which affect the stability of negative charge? So let's see. Factors affecting the stability of negative charge or stability of base or stability of base. So one thing is clear, more is the charge on any species, or we can say more is the charged species. Highly charged species are less stable than the neutral species. So one thing is very much clear, that charged species are less stable than neutral species. So this thing that we should keep in mind. All of you, we all know it, but to explain these factors, to explain this one, we should keep in mind that charged species are no doubt less stable than the neutral species. For example, if we say H2O, or if we lose this losses of one of the proton to form a this OH minus, and again it losses a proton to form a this O2 minus, O2 minus. Okay, so which is more stable? No doubt this is neutral species, this is more stable, and then it is highly charged, this is least stable. So what are the factors which affect the stability of negative charge? Anything which stabilize the negative charge, that will increase the stability. Anything that stabilize or neutralize the negative charge will increase the stability. So one of the factor, electronegativity. For example, if we have seen in the previous various acid-base reactions. So what I have written. So suppose if electronegativity increase, then what will happen? If electronegativity will increase, then size will decrease. Size will decrease. It means the negative charge is much more pulled towards the nucleus, and stability increase. So stability of negative charge increases, and if stability of negative charge increases, means base is more stable. That is, stability of base increases. Stability of base increases, and stability of base increases means its strength will decrease. Weaker is the base. It means base is weaker. Weak base. Weaker is base. So for example, I have written 4 acid-base reaction previously. So what are the various base negative charge species I write? Fluoride ion. Then I write hydroxide ion, then this NH2 minus, and then CH3 minus. So out of this 4 species, which is most stable? So what I told you, the most stable, this fluoride ion is more stable than this. Why? Because fluoride ion has the highest electronegativity. If it has the highest electronegativity, then this negative charge is more pulled towards the nucleus. So this negative charge is much more pulled towards the nucleus in comparison to this, and in comparison to this. So it means negative charge is much more neutralized in case of fluoride ion in comparison to this. So this is the most stable, least stable. Okay, this is weaker is the base, weak base. Fluoride ion acts as a weak base, and this acts as a strong base. Okay, this is one of the factors. Okay, now second factor, that is the second factor which determines the stability of negative charge, that is the polarizability. Now suppose I write from top to bottom. This is from left to right. This is from left to right in a periodic table. Suppose I write from top to bottom, fluorine for fluoride ion, then bromide ion and iodide ion. Now, out of this, which is most stable, or which is weakest base, which will act as a weakest base here, which is able to form a strong bond with proton, that is strong base. Okay, so which is weak base and which is strong base in this case? Now suppose if we see, now polarizability means what we have to see, ultimately we have to see that where the negative charge is much more neutralized. So the negative charge is neutralized, in which case no doubt this has the size from top to bottom in periodic table, size increase, and if size increase, then the polarizability of the ion, that will increase. So larger is the size, then polarizability, more is the distortion of the electron cloud. More is the distortion of electron cloud means the charge is much more dispersed. So here in this negative charge iodide ion is much more dispersed. So it's like this. So here the dispersion is higher due to the higher polarizability. So more polarizability, and here least polarizability, and that's why it is most stable. And weakest base. This is weakest base, this is the strongest base. So these are the two factors. Now third factor. Third factor is, suppose, resonance. Third one, resonance. We know that due to resonance also the charge is dispersed. The delocalization or dispersal of charge takes place due to the resonance. So as the resonance increases, more is the dispersal of charge, and we know that stability increases, and if stability increases, strength of base, basicity or strength of base decreases. Strength of base that decreases. So suppose I write, suppose this is one of the species having a pair of electron, and another species, and next species. Now out of these three species, which is the weakest, which is the most stable? No doubt here there is no resonance, no delocalization of this lone pair of electron. Here delocalization due to this one of the pi bond. Here delocalization due to the presence of 2 pi bond. Delocalization of this lone pair of electron, that will occur due to the 2 pi electrons. Here the lone pair of delocalization occur due to the presence of only 1 pi electron, and here there is no delocalization. So no doubt this is most stable. Most stable means weakest base. This will act as the weakest base. Means this will not able to donate its electron pair to the proton easily, but this can donate it. So another factor which can be written, that is the inductive effect. Inductive effect, or we say that electron withdrawing effect. Electron withdrawing group effect. And suppose if we have a CH4, one of this negative charge species, another negative charge species having one electron withdrawing group, that is chlorine, another species having 2 electron withdrawing group, that is 2 chlorine atom, and next one having the 3 chlorine atom. So all of you can see that here this species having 3 electron withdrawing chlorine atom, that will neutralize the negative charge much more in comparison to this. So this will stabilize. This is much more stabilized in comparison to this. So this is most stable and this is least stable. Most stable and this will act as a weakest base. So this is weak base. This is weak base. Okay. In the same way, another factor that is the S character. S character. We know that as the S character increase, electronegativity that will increase, and electronegativity will increase, then negative charge will be more neutralized. So as the S character increase, negative charge is negative, means electronegativity will increase. Electronegativity increase, and electronegativity increase means negative charge is more neutralized, and stability increases. Stability will increase. For example, suppose I am taking 3 examples. Suppose I have ethyl anion, and then having this carbon having sp3 hybridized, then this carbon having sp2 hybridized, and this one sp hybridized. So no doubt here this carbon is more electronegative in comparison to this. That's why this would be here, the negative charge is more neutralized. So this is most stable. Negative charge, and this is weakest base. And last one, that is the aromaticity. So all of you know this. As the aromaticity increases, the negative charge is much more delocalized or much more dispersed. So stability increases, basicity decreases. Base strength decreases. Negative charge is neutralized. So suppose I take example. Cyclopentadienyl cation and cyclopentapentane ion. So out of these two, no doubt here this negative charge is in conjugation or delocalized with this pi electrons, pi bond, and that's why this is more stable. Negative charge is much more dispersed, so that will act as a is more stable, that will act as a weak base. So here this will act as a weak base. More stable and weak base is more stable. Okay, so these are some of the factors which determine the basic strength of the any species. So hope you are clear with the difference between the nucleophile and the base. What I told you, this nucleophile which donate its pair of electron to some carbon center, electrophile, and base which donate its electron pair to the proton, and base are very much related to the acid-base reaction. These are the Bronsted base, whereas nucleophile, these are the Lewis base. So when we see the base, then we should think about the acid-base reaction. We should think about the pKa value. We should think about the conjugate acid-base pairs. We should see that we know that the strong acid, it forms the weak conjugate base, means stable anion. Okay, thank you. So in next lecture we will see about the difference between the nucleophilicity and the basicity. Thank you.